All right, let's get into our first data talk. Just as a reminder, this is the kind of talk that you're assigned to do. Basically, I found papers that I think look interesting and they illustrate some chemical aspect of how things go together. And so this will also give you ideas for your discussion. After this, I would like everyone to write a question and comment up on the board, and I'm going to arrange it by chapter, although if you aren't sure which chapter it fits in, just pick one, you know. So, and then we'll go through our questions and comments. I'll try to answer your questions, and we'll just compare our different comments that we have. So, this is one of my things, and this will be on the test in the sense of I'm going to try to give you Atkins problems that relate to some of the concepts that are in these papers, okay? So this actually supports several of the things you're going to be asked to do. Anything that you write down today, of course, is valid for the open book of the test. I'm not going to be quizzing you like on details of what's going on, but what I might do, and one of the reasons why I don't want you to have like printouts of the slides, is I might give you a slide that I show you and like take out part of it and ask you to interpret what that part is, like give you enough information so you can figure out what's going on. I just don't want you commenting exactly what the title of the slide is in the paper, you know, things like that. So that's why I'm not giving you these papers. The concepts, when I show you a graph, I want you to like interpret it, not memorize it, but be able to see where the chemistry connection is. And so as we go through, if you have questions about that, let me know, and I can explain a little more when we get to it. Okay, so this is, and remember that we're actually bridging two different books. Remember that my book was actually really based on, it's not really mostly my ideas, it's mostly R.J.P. Williams' ideas. You know, so I mentioned this book earlier, The Chemistry of Evolution, and I do want to give him credit. He's written a bunch of books like this. This is my favorite, but this is a book that it took me like weeks to read this book. He has a very dense style, and I was like, oh, I should interpret this and like bring it up to date and connect it to other things. And so that's what I did with my book. And so I'm not making you read the orange book, I'm making you read my book, and hopefully that's a better experience than forcing you to read the very dense book. But the thing about R.J.P. Williams is he builds everything he says on chemistry, and he has a lot of physical chemistry actually in it. In fact, I might show you a figure from his book right now. And the really cool thing, I didn't really plan this. There's a couple of reasons philosophically why it makes sense. But we're going through the Williams/my book and the Atkins book. Those two stories actually do sort of go together, because in Atkins, so far, we've talked about enthalpy and entropy. And it turns out that those are big in the story of, you know, why did the universe cool? We already talked about that. But also, why did oxygen get bound up? That comes from the enthalpy of the bonds that are being formed. And as we go through, we're going to eventually talk about phase diagrams in the next chapter. We're going to talk about solubility and equilibria in chapter 4 of Atkins. And that goes exactly with chapters 4 through 5 of my book. And so actually it's kind of interesting that if you look ahead, we can talk about how Atkins and the history of the world sort of line up. At least we can bring out certain calculations from Atkins. And so we're going to be mentioning some of these things. We've already mentioned the cooling upon expansion thing. Phase diagrams are great, and we'll get into those with chapters 3 and 4, and those will go right along with the first thing. So test 1 is going to be like, well, test 1 is going to be sort of right here. We're going to have big K's, we're going to get through big K's for test 1, and test 2 is going to involve E calculations and little k's. So it all fits together, and one of the things we want to do in this data talk today is to fit it all together in another way, and at the end of class, your presentation will be sort of fitting lots of things together like this, shaped around finding two papers that are kind of like the papers that I show you here. So we have all three laws of thermodynamics that we're talking about. We talked about actually laws 2 and 3. when we went through the entropy discussion previously. Heats of reaction play a big part, because if you're talking about bonds, you're talking about how much heat is released when that bond is formed. That is the definition of bond dissociation energy. How much energy, how many kilojoules do you have to put into that bond to break it? That's not about entropy at all. That's just about the energy you have to put into the system, or the energy you get out of the system when you break it. I'm sorry, I want to make sure I say this right. The energy you get out of the system when you make a bond, as opposed to the energy you have to put into the system to break the bond. This is actually one of the fundamental things about chemistry that is actually kind of hard to get, because you think of a bond and you think of energy in the bond. That's not quite true. It takes energy to break the bond. When the bond is made, it releases energy because it's more stable. And you want to get that kind of concept. That's the kind of concept that I'm after, that I'm going to have some test problems on and things like that. Basically, delta H for bond formation is negative, because that means that heat leaves the system when you form a more stable bond. So we're going to form these bridges, and we're going to focus on explaining things at the molecular level. So this is actually the original figure from R.J.P. Williams. This also showed up in A World from Dust. It's been modified, and the thing about scientific data is you can make your own version of a new table, and it's not copyrighted because the data is not really copyrighted once you publish it. You can make a new graph of the same thing. That's what we did. So over time, we started talking about why did things clump together. We sort of skipped over how did hydrogen, well, we said that it happened. We didn't really show you how it happened. But we had hydrogen and helium, and they were fused together in stars to form larger nuclei. And so you see, this is the current distribution of the amount of elements in the universe right now. So which is the element in the universe right now, 13.7 billion years after the Big Bang? Can you read this graph? It's a little small. But which is the element on the top? Which element predominates in the universe today? The highest number here? Yeah, it's still hydrogen. We're still mostly hydrogen. We just have these other things that have turned out as well. And this is, by the way, is a log scale of the relative abundance in the whole universe. Now, if you'll notice, lithium, boron, beryllium, those are really low. And there's actually a really interesting thing about the universe. This is they're hard to make. They actually fall apart easily. And this is the part, there's a little bit in the book about how you get past this. This is actually a problem for making the heavier elements, because these lighter ones, you have to mash them together, and if they fall apart before you can make carbon, then you can't make carbon. It turns out that we live in a universe where there's a special energy level in carbon that lets this happen. But you can see right here, because these are low, that's weird and that's a problem. But we are able to get past that problem. We're all made of carbon. Obviously, it can be made. But so the whole thing is, as you get bigger in atomic number, you roughly go down as far as abundance in the universe. And if you look at this is another R.J.P. Williams thing, and it shows the most abundant elements in the human body. And if you look at this, it's not exactly the same. We use less hydrogen than there is in the universe, but we use a lot of carbon and oxygen, and they are like the next most abundant elements. If you look up and down this, you can see that, and the elements down here, iodine, selenium, manganese, and cobalt, what do those all have in common? They're sort of low on this graph. Here's manganese, and it's probably the biggest one. And the selenium's like way down here, So we use the atoms. If you look at these, like calcium, phosphorus, and things like that, you'll see that they tend to be on the top half of this graph as far as abundance. We don't use thorium because there's not enough of it around for us to have evolved to use. So you can look at this graph and say, roughly speaking, most of the periodic table is not really accessible to us. We can only use the elements that we've been able to make, that there's been time to make in the universe. So there's our friend hydrogen up there. These are the elements that will tend to be made, that tend to be used in the body. And in fact, it even goes so far as the ones on the lower half of this graph tend to be used in trace amounts, while the ones on the upper half of this graph are the ones that you can get grams of, carbon, nitrogen. Look at that, carbon, nitrogen, oxygen. There's an abundance of those. There's just less silicon and calcium around. So one of the things, why don't we have silicon-based life? Well, one of the things is there's a lot less silicon in the universe. There's obviously a lot of it because we've got a lot of it under our feet, but is that part of the reason why carbon-based life, and if this is true for us here on this planet, isn't it true everywhere else in the universe as well? And that's why we should expect carbon-based life rather than some other form of life that we don't really know how the chemistry would work. That's just an argument. It's a simple argument, but it's an argument from abundance. If you look right here, like titanium, there's not much of it. Even though it's small, it's one of these things that dips. It's scandium right here. We don't use that in biochemistry, not even in trace amounts. So you can argue that we use what was there. We use what was on the table. And there's another one, that's aluminum. Aluminum is actually fairly abundant and small, but we don't use that either. There's some other arguments for why we wouldn't use it beyond its simple lack of abundance, but it's not the most abundant element, so why would we use it when there are other ones that are there? And there's silicon right there, showing that silicon is less abundant than carbon. And so we just want to think about these things. We want to think about how much of the element we have, because we can calculate this, and it's pretty much universe-wide. Selenium right here, that's actually got some unique chemistry. It's on the line between metals and non-metals on the table. And it's right here. And you see how it is the element in the human body, we just barely have some. We use a little bit, it's even a question of, is it really essential or not? Like if you have a selenium-free diet, you might not even notice. So we use it, but we don't use it very much. And that's actually going to come into one of the papers we're going to talk about. Okay, so the thing is, we have all these elements, and it took until Dmitri Mendeleev came up with the periodic table when he realized we got enough data for the elements, chemically speaking, to say, hey, it seems like there's patterns to this, that every 8 elements we have repeating patterns to how they react and how big they are. And he was a card player. So he literally was playing a game of solitaire. He put all the elements down on his table as cards, and he slid them around to figure out, hey, we have these repeating patterns. Now we have computers that can look at the same data. So what would happen if we fed a computer the same kind of data that Mendeleev had, updated because we're using all the atomic numbers and weights that are accurate, so the computer has a bit of an advantage. But if we just had a computer that was playing a card game, sliding these cards around on the table and putting similar cards together, okay? Could it be able to recreate what Mendeleev did? Could it discover the periodic table trends in it? So we're going to use something called principal component analysis to do it, and I'm going to have a guest appearance from Dr. Pierce's data. Have any of you taken the class with Dr. Pierce that she's talked about PCA?
Yeah, she talked about separation science.
Separation science? Okay. And do you remember what the topic was? Because I might show it here.
It was like biodiesel, I think?
Yeah, exactly. I'm going to show you some of her data. And so the thing is, she's the expert, so I may get some of this wrong. Correct me if you catch anything. But I'm going to describe what Dr. Pierce does, because what she does is she organizes complex data using a computer to basically put points that are more similar close together on the graph, points that are more different farther away on the graph. Exactly like the periodic table. So I actually got these slides from Dr. Pierce about what it is. And basically, if you have any kind of data, PCA is a way of organizing data. Okay, so if you have just a bunch of samples and you're measuring 2 variables, this is completely abstract. And you see, so you have all these numbers, and I look at these numbers and I don't really see what's going on. I can't see any pattern in the numbers. Maybe I can try to put them on a line and I can try to figure out whether there's a pattern, but how do I do that? How do I do that efficiently? There's a way to do it mathematically, to organize the data and to see if there's any kind of correlations or organizations beneath the data that you can see mathematically. So it's kind of breaking them into groups. So you can, each of these variables, you can organize them. You can organize them on a 2-dimensional graph. And if we do that, you can start to see, okay, well, there's sort of a linear relationship between these, but more than that, how many groups of data do we have? Probably we have one group of data up here, we have one group of data down here, maybe there's two groups that are sort of slightly separated. But when we look at it this way, you can start to see the groupings in the data. And the PCA is a way mathematically to figure out what the important thing about PCA is it figures out the axes that you should use to relate these two things. Right here, you can have, if it happens to be that your X and Y axes are how the data separates in groups, great. But you can only do this in 2 dimensions. I can't do it, maybe we could do it in 3 dimensions if we had a computer, but more dimensions than that, more variables than that, we don't have any hope. But there's a way that you can do this mathematically. You can see it in 2 dimensions. The computer can do it in multiple dimensions beyond that. And that's what PCA is. So like right here, we have a 2-dimensional arrangement. We have a linear relationship between the data. But notice that the linear relationship is not a perfect line. There is the obvious one that we can see. We can also see that there's some spreading of the data in 90-degree direction as well. There's a width to the line. And so what PCA does is it says, okay, this is the principal component 1, the most variation among the data. If I draw a line through it, I get the most possible variation through the data. And if I draw a line in this direction, I actually capture another dimension of the data. I capture variation along the width rather than along the length. So secondary, this is principal component 2, but the data does sort of group. You can see that like this line is very variant from this group is in principal component 2. It's sort of off the line, the principal component 1 line. Basically, it's drawing axes through the data to try to find the maximum amount of variation, and also to have the variations be different from each other, separate from each other. These are very separate because they're 90-degree angles from each other. So what you do is, and so this is about how all the math works, and this is where Dr. Pierce will sort of talk about what you're basically doing is you're redrawing the axes, and you're scoring each point by how far away it is on the redrawn axes. Like this variable gets actually sort of redrawn on this. If you do that, and if you take the angle of the axes, the new axes have an angle, and you take the cosine of that, and that does math stuff for you. That helps you to organize what's going on. Realize that this is completely mathematical. Okay, so you're looking for the maximal spread, the variance in the endpoints. This has a lot of variance along this axis. This has less variation, but there's still it's a lot of variation, and it's a different thing. So you can do this. This is 2 variables. You can do this for a large data set with thousands of variables, because what it will do is it will find the most widely ranging axes that will fit that 1,000-dimensional line, if you want to think of it that way. So this is one of the things where math really gets you something. You know, you can actually deal with thousands of variables, and you can find 2 principal component axes that will be the way that it varies the most. So, for example, like if you take the data, you take the scores now, and you separate them out, and you can see now you still have your 2 groups. This was your group on the northeast corner. This was your group on the southwest corner. But you've sort of spread them out differently because you spread them out according to their variation. And so you can take the angle of the spread out and you can use that. And this is where I start to turn to Dr. Pierce for exactly what that's for. But the main thing is you can do this for any number of variables you have. So you can take a gas chromatograph. And let's say that she just took a gasoline sample, ran it through GCMS. Each of these is a different molecular component, but you have no idea what it is. Or even if you know what it is, you don't know which ones are important and which ones aren't important. PCA lets you find out which variations are important, so you can group the spectra that you get, or the chromatograms that you get. You can group them into different groups. And realize each of these lines, each of the readings is its own variable. And so we're literally taking hundreds of variables in this case. and we're taking 210 gasoline chromatograms, and yet the computer is going to be able to group them just like we grouped the two samples on the previous slide in 2 dimensions. So they had A, C, M, S, and T samples. These are different gas stations that she took gas from. Okay, so you can kind of guess, these are gas stations from around here. Anybody want to guess which gas station is one of the letters? Like S is Shell. What do you think the other ones would be? Yeah, A is Arco. What's it?
Chevron.
Chevron. I think M is Mobile, and T is Texaco, I think. We'll have it on another slide. The main thing is, of those 5, if you know that if you've gotten gas, which of those 5 would you think is different from the others? Which is a different kind of gas station, sort of the cheapo gas station. It used to be they wouldn't even collect credit cards. You used to have to pay cash, but they changed that. Or debit card.
Texaco?
No, actually, that's one of the big chains. This is a more regional chain. So Texaco and Shell, you go all around and you see those. But this is a local sort of cheapo gas. They're known for having lower prices. Which one? Oh, the Mobile. Actually, that's a large chain as well. So, no, it's actually Arco. Arco is the local brand, and it's a cheapo gas. And it used to be really prominent when I first moved here because they wouldn't even take credit cards because it would save the money, right?
Yeah, no, because I know from our way they don't even use the articles.
Right. Yeah, and so if they have the lower prices, sometimes people wonder, is their gas different from the others? Or maybe Chevron's gas is different than Shell's or something like that. And so if they have some little additive in there, this is not going to pick that up. This is going to pick up an overall difference in the shape of the chromatogram you get. Okay, so here's the chromatogram that she ran, and this is from one sample. And she put it through, and this is what we saw. And one of these is not like the others. If you see it's Tesoro, not Texaco, Chevron and Mobile, they all group together nicely, all the different samples. The computer can actually tell that Shell is Shell and Tesoro is Tesoro. And if you look at this, these are all closer together. The one, if you had to pick the odd one out, is the cheapo Arco gas. And so there's a question, are they putting a little more ethanol into their gas, which is one way to save money and things like that. And of course, they didn't know what Dr. Pierce was doing this. He was being a completely blind test of this. But that's really cool. But basically, the thing is, you can put the different types of gas. There's some difference, and they like there is a difference. Chevron probably has a particular additive, and that shows up in a certain way on the chromatograms. But it's a minor difference. There are more minor differences between these. And you can also say Chevron's more like Mobile, and Shell is more like Tesoro than Shell is like Mobile. You see that? But Arco's the one that's all the way away from everyone else. Also, they have more variation within the amount, which seems to, they're probably cutting corners a little bit when it comes to costs. So this is what, so that's what you can do, and that I like it when you can do science and it fits your intuition. My intuition was already Arco's a cheap gas, and there it is. It does show up differently. Have you ever heard about there's 4 personality types? I don't know. There's all sorts of problems whenever you try to divide people up into 4 groups. But have you ever heard of 4 personality types? There's actually several different ways to talk about that. But maybe they don't teach it anymore because it's too simple. I know my psychology friends hate this theory. But the question is, are there really, and people draw the 4 types differently. Myers-Briggs, you have the introvert, extrovert. I don't know whatever you are, but I'm definitely on the introvert end rather than the extrovert end, right? So I'm an I. And notice how they have 4 different characteristics that you can be, so you can be one way or the other. So basically, are there really 4 personality types? Let's take a bunch of data and let's give it to the computer and see how many groups the computer makes. And it turns out that the computer actually organized people into 4 groups. Now there are 4 different groups than any of the other 4 groups, but it seems like the number 4 does make sense. And they came out to these, they put these together and they clustered them. It's not a great clustering, but they actually, let's see with the 4 personality types. 4 distinct personality types. There are different combinations of these. I think each of these is a different way that you show up on the 5 characteristics. And so basically the green people are low on, are low on neuroticism, they're low on openness, and they're average on the other things. The average person is low on openness and high on the other things. So you see how each of these has a different shape to it. But what it's saying is it took a ton of data, and it did come up with 4 different groups. You have the reserved group, the role model group, the self-centered group, and then the average group. This is just the computer organizing the data for you. So, if we can organize gasolines, if we can organize personality types, what if we tried to organize elements? So what they did is they took these fundamental ideas, atomic weight, atomic radius, the first ionization potential, the first EA, electronegativity, I think, but no, this is electronegativity. I don't remember. It's an energy. It's an energy of activation, maybe. Anyways, what do you think? Oh yeah, that's it. Thank you. So ionization potential, electron affinity, and electronegativity. These are related. Each element has its own one of these, but these are also fundamental physical chemical properties. We're not adding anything else into it other than these numbers. What would happen if we gave this to the computer and had it organized? This is what it does. And at first it doesn't look like a periodic table, but then you start to look. Oh, it's putting all of the halides over here in blue. It's putting all of the semi-metals in the middle. And actually, if you look at the colors, we're not dealing with transition metals because I think the D block will just confuse it. But dealing with just at least the upper part of the periodic table, we get the same groupings. Gray is in the same place, blue is in the same place. And of course you don't use the noble gases because those are just, well, I think you could, but you might not have good data on them. But definitely everything else comes about as the colors. It's a little tilted and twisted because it had no other information. But it wasn't constrained to do this in any way other than by the data itself. And so just from that, it slid those around on the table and the computer recreated the PCA. By the way, look at this, principal component 1, principal component 2, and you can say how important they are. Principal component 1 explains 60% of the variance. Principal component 2 explains 23% of the variance. And so this ends up, this tells you about how much of the variation is captured. These should add up, maximum these can be is add up to 100%. So these are pretty good components actually, if you look at this. I just love this because it shows that this comes from the data. A completely objective and in fact a completely computational method will actually develop the same thing that Mendeleev did. It's just that he was working with worse data and it took him a little longer, you know. But it's the same thing. This is a fundamental fact of the universe. That's one of the main things about the book. We start from that and we move on. Okay, so if you start from that, you have these periodic trends, and you can find there's some things in the book about how the periodic trends show up. One of the ways they show up is with enthalpies. Right here, this is a case where now we're dealing with transition metals, and we're dealing with these 6 transition metals, and they're binding into the middle of this complex carbon scaffold. Those of you who've had Dr. Lewis, this is her area, inorganic chemistry, and she is all about how metals and organics bind together. And so look at this, each of the 6 frameworks, they're putting the metals in a framework, and they're seeing how the metals bind carbon monoxide. Carbon monoxide will bind each of them, and they find that it follows the Irving-Williams stability order. And by the way, this Williams is R.J.P. Williams, right there. So we talk about the Irving-Williams series. I think it's in chapter 2 of the book. This shows you how it comes up in enthalpies of this weird chemical reaction. They just have this organic framework, and they put different metals into it. The different metals can just fit right in there. They have one open site for binding CO. Those of you who have studied, if you remember, hemoglobin, binds CO in the same exact way. It has an open coordination site, and carbon monoxide binds to your hemoglobin iron. So yeah, carbon monoxide will bind all of these, and you can see that they even have the crystal structure, so they even have the bond lengths for each of these. Everything else is the same except for the metal in the middle. And when they do that, they can actually measure the partial pressure of the carbon monoxide and how much is bound to the metal. And you can see that nickel and cobalt, it binds really tightly to. At a very low partial pressure, you get a lot of CO binding. Zinc, on the other hand, it's very low binding. So this is much slower and lower binding to zinc. And you can pretty much put them in order. You have nickel on the top, then cobalt, then iron, then magnesium, manganese, and zinc. And they have the numbers right here for the CO binding. Realize this is the formation of a bond between the metal and the carbon in CO. And they have all these things that we don't really, they like model it. This is the real data that I think that we should focus on. Notice the letter there. It's a little small. Can you see that? Negative Q. So negative Q of the binding in kilojoules per mole. They've measured, or actually this is a prediction. No, this is actually a measurement. I'll take it back. These other, on the other side, they're predictions. But these are actually the measured heat coming off of it with calorimetry. So this is the enthalpy of the thing binding. And you can see nickel's on top. Nickel releases the most heat. It also has the shortest bond. So remember that bond length and bond energy are related. They can talk about the angle a little bit and how much capacity can it bind overall. But the really important thing is if you look at these Q's, the heat of binding goes along with this graph, the amount of binding. If you have more binding, it releases more heat, it binds tighter, it has a shorter bond. And all of it goes in order of the Irving-Williams series. I didn't show it, but it shows up in your book, and you can look at that. And you can see that zinc is on the end of it. We don't have copper. If we had copper, I think it would be, it's possible they couldn't do it because it bound so tightly, it would be irreversible. So this is the idea, that you want to be able to look at data like this and see the Irving-Williams series and maybe compare it to the book to see. But if you would, you could predict that. You could open up the book if you have a case like this and you want to know which of these six will bind tightest. Look at the Irving-Williams series. According to that, nickel binds tightest to most things in general. And you would predict nickel would be on top. Okay, so the last thing I want to talk about is I want to talk about the this place. And this is where we start in the book. This is Mono Lake. What I like about this picture is it shows the water, earth, and space. And the thing about chemistry is there's connections between all of these. The stars made the elements that you see down here. The water hosts the life, and so the water provides the chemistry, but the water also includes a lot of the material from the rocks, okay? And this is, to give credit where this came from, this is a National Geographic letter. It's how they do Instagram. I actually recommend it. They take great pictures. And they're limestone towers and islands of tufa, carbonate minerals in the water. High carbonate because all the mountains go in there. But you remember what else is high there? The element, other elements that are in rocks that end up concentrated there, arsenic. And as you know, arsenic is a poison to us normal humans. And I talked a little bit, I think I have this in the book, I don't think I cut it, about how a bird, there's so much calcium carbonate in here that a bird that sits there too long will actually become calcified. And these are pictures of birds that the calcium carbonate has hardened around them, just kind of like those little towers of calcium carbonate. This is like they've been literally turned to stone. It's called a calcifying lake. Okay, so how can anything, there aren't, I don't know if I got this right in the book. I don't know if I said there are no animals in Mono Lake. Well, they knew at least when they knew there were two, and by animals we mean really small worms, okay? But they actually went to Mono Lake, and since that time, they actually found more worms. And this is one of the things that they did. They sequenced the worms, and they found that they were extremely arsenic resistant. And in other ways, they were able to tolerate Mono Lake's really weird chemistry. And they even found some genes that suggested how they would be. But basically, there were 2 known species before 2010. Now there are 10 known species. But the other thing this says is the whole thing about Mono Lake was Felicia Wolf-Simon's idea was that they would actually incorporate arsenic. So here's a case where it would be advantageous to them if they could. You know, they're so around arsenic, why can't they use it? Yet even in this case, the bacteria could not use arsenic. And that seems to imply arsenic just can't be used for DNA. We're like stacking the deck as much as possible. But it looks like at least for a phosphate arsenic hybrid, you can't make DNA out of arsenic because of basic chemical reasons. And even these support that conclusion because they do not incorporate arsenic, they resist it. They found ways to get it out of their system, to build a wall against it, rather than to come to terms with it and to use it for their DNA. The other thing that it has is selenium, and this is really a fascinating paper. It's really written informally, like the guys like cracking all these jokes and things like that. But that's why they call it a perspective. But it's a scientist who studies selenium, including in Mono Lake, and he found some bacteria in there that do some really cool chemistry. So he found Bacillus salinitireducens. So it reduces selenium. It reduces selenite, in fact. Selenite is SeO3 with 2 minuses. So what it does, if you're reducing it, you are removing the oxygens, you're taking electrons from it, and you're moving it down in number. So you are reducing the selenite, and actually, it's an electron acceptor. I got that wrong. It's an electron acceptor because you're going down from Se4 to SeO. So I need to change my slide. I just made this yesterday. But when all the electrons are added to selenium, then you go down from +4 to 0. And then you make selenium metal. And so it also uses arsenic. And so I think the bacteria can survive. But these are anoxic bacteria that don't use oxygen. And they make sure you have that right in the writing down, that it's an electron acceptor, not an electron donor. And that makes sense because it can also use arsenic. So basically you can pass electrons through these things. Once you pass electrons to them, you end up making the solid metal. And if you look at them under a microscope, when you feed them a lot of selenite, they will make these little nanoparticles of selenium-0, metal selenium. They have 2 different mechanisms too. They have one mechanism for producing them outside and a different mechanism for producing them inside. They do it both ways. The final thing about selenium is black when it's in the tight crystalline form, but it's when amorphous, when it's like not carefully packed together, it's actually red. And you can actually see organisms that are doing this. This is a purple bacterium, but it does the same chemistry. It reduces selenite to elemental selenium metal, and it turns red. And if you see the treated right here, if you look at here, so if you look at the control versus treated, let's see, the start of cultivation, and then you can control strain is in a medium without selenite, and the treatment is a medium containing selenite. If you look over here, it's making the selenite, and it's actually being red. It's turning red when you have treated it with selenite. Yeah, and in fact, you see that the control actually turns a little red before that. I wonder what's going on with that. But the main thing is, after 8 days, you get the clear, those are selenite particles. And so the bacteria is doing really cool chemistry with selenium. This bacterium might be using selenium in interesting ways. I would look at this bacterium. I don't think it could incorporate arsenic into its DNA. then maybe you can incorporate selenium into its proteins, because we do that. We actually have a selenium amino acid that we use in Biochem 2. They talk about the one particular amino acid. So you actually, technically, you have more than the 20 amino acids. It's a post-translational modification. You turn a serine into a selenium serine, and you basically use that for a particular chemistry. So, I would wonder about, I think it'd be fascinating, because there are probably people investigating that right now. They're definitely doing something with the selenium, because they are taking it and reducing it down to the elemental metal particles. All right? So that is my version of the data talk and things like that. What I would like to do is I would like to invite you, and just want to remember, on Monday we have chapter 2 homework due, and we will start chapter 3. We'll have 2 days on chapter 3. We'll follow this pattern again, and we'll have 2 more days for chapter 4, and believe it or not, we're halfway to test 1. I guess after today, yeah, we're halfway to test 1. So we are getting into things. Let me know what questions you have when you go through these things, but this is the idea of what you want to do.